Hello. So we have only 1 hour lesson now because of the trip. I wonder where the bus goes from. Maybe somebody is here who goes to the trip, but it doesn't look like it. Maybe they went to eat.
I thought the trip was yesterday.
No, it's today at 11:15. It's finished like usually. So we are almost in the end, and now we have this factoring polynomials, algebraic identities. Wow. I managed to pronounce it. I already showed you this. What we can find from the equation book, technical formulas. And here are these dependencies and the Pascal's triangle. And then we can test it because there's some exercise about it. Expression, blah, blah, blah. You have different degrees of polynomials. Sorry, there is this kind of I should correct that. Factoring polynomials, so rewrite the polynomial. So there in the exercises is you either modify it this way or this way. Then, for example, something like this, you write this with the roots, this one as well. That is said in the, it's not there. Let's see. I'll show it to you then also from the equation book. But these equations you have in the technical formulas. Here is also geometrically the difference of squares. You can take a look at it if you want. And what else? Pascal's triangle. I'm not going to talk more about it because I'm not an expert on that. We can just test it then. So let's start the exercises. Here you already get to simplify. It means that put it into the form that is there in the, for example, in the technical formulas. And here you can test on the exercise 2, the Pascal's triangle. And there aren't that many of these, so we can just go through, and then we can also try to do the deriving the second degree formula, but let's see. We can also do that next week. Let's see what we manage to do now. That's quite loud. So in technical formulas here, in the page 8, you can find this. And then here you can find how to express a second degree equation with the roots. So these are basically the procedures we are supposed to practice now with those exercises. Oh yeah, the light. Okay. Thank you. So obviously this is after this. This is so I'm in the technical formulas page 8. And then again, we're after this. And what we were after was Mhm. So I've done it the same way here. The first in the power of 2. Then the both of them multiplied, and there's a 2 to multiply with, and then the second in the power of 2. And this is it, and it doesn't mean anything. This is just the way you were supposed to do it.
How do you know to use a squared minus 2b rather than a minus b? Just because there's one bracket.
How do I know to use a squared?
So on 5, the question b, why couldn't I just do a minus b to the power of 2?
Do you mean like why does it have to be this kind of sentence?
Yeah.
Because this is something that they derived earlier. So this becomes this. And why does it become that? I can do it, for example, with this. Should I do it with this or this? I do it with this, yeah? Okay. So this, what it means is this. Oops. Thankfully, I found these pens. I was so happy. It's the first time this autumn I've seen them in the storage room. I took many. Okay. So this, of course, in the power of 2, it means this, yes?
Yeah.
Because, for example, 2 in a power of 2 means 2 times 2, yes. It's the same thing. This in the power of 2 means this multiplied by this. Yes. So then how you multiply this if you have there 2 terms? You have to multiply this first with this, and then this with this and this. So then you multiplied everything. So first I would multiply this with this. So then I multiply this with this. So then I get, for example, this way. Minus 2. Then, so now I multiplied with this, these both. Now still with this. So minus 2 multiplies this. And minus 2 multiplies minus 2. Okay. Now I've done it properly, yes. Okay, now I start to make it to look nicer. So this one, this multiplied by this is obviously this in the power of 2. I make it to look the same as this sentence here, okay? This in a power of 2. Then I had this multiplied by minus 2. And again, this multiplied by minus 2. So obviously now I have to put, I calculate them together. So I add them together, yes, because there's 2 of them. So I know that there's 2, and then there would be a sign minus because they both have the minus sign, yeah? This is where the sense for this comes from. 2 times minus 2 times this times the latter term. So 2 would come because there were 2 terms, and then this 2 would come because I'm always multiplying here the 2. Yes?
Yeah.
Do you see the sense or?
Yeah.
Okay, cool. And then I still have this here. So obviously minus 2 times minus 2 is the same as minus 2 in the power of 2, which is 2 in the power of 2. Yes?
Yeah.
Okay, so now this looks the same as this, yes? They are the same. This is not a great pen, this red one. It already feels like there's not enough. And then I just calculated open like I did here. Yes, so it's the same, of course. This in the power of 2 is 5 in the power of 2 times W in the power of 2. 5 in the power of 2 is 25.
Yeah.
Minus this 2 times 5 is 10 times 2 is 20. And then, well, this is 4. Does it make sense?
Yeah.
So actually none of these equations that you find in the equation book, they aren't anything magical. They are just something somebody calculated this open and realized that it behaves like this. So you don't have to do all those procedures. You don't have to write it first like this. You can just write it straight like this. I had to do one sentence more here when I didn't use the equation.
Okay. I thought I had to, take 5W minus 2 and somehow plug it into A squared minus 2B plus B squared BX. Like take the 5W and replace the A with 5W. Then the B is replaced with 2. But,
yes, that's true.
It's just the same thing.
It's exactly the same thing.
Okay.
It's exactly how you said it.
Yeah, I understand that. Thank you.
Okay. So in the maths, there never happens anything like magical. Everything follows all the rule. There's no exceptions like in languages.
Yeah. I think I've never done the formula here.
Okay.
I have never seen that, but this part, where you go through.
Yes.
The part you've done, but I've done that a lot. I remember that very well.
Okay, cool. Yeah, and all then engineers use just formulas. Yeah. Or mainly they use Excel where the formulas are already in.
Okay.
But then you should somehow know how they were formed as well. Obviously here I want to use the formula A plus B in the power of 2. Oh, how can this be so bad, this pen? I was so happy with the pens. Now I would need to use the Pascal's triangle if I put something in the power of 3. If I take a line from the Pascal's triangle, let's just put it here. I write it, for example, like lines. I would know that something in the power of 3. I would look at the line and I would see the 1, 3, 3, and 1. And then I would need to start doing that way. So first, have this in a power, in the, then I have something here, and I have, to check so that I don't make any. Yeah, because I have the 3 there as well. Okay, maybe it's better to write this open first in this way. What this would mean is a in the power of 3 plus 3a in the power of 2b plus 3ab in the power of 2 plus still b in the power of 3. That is what this means there. And now I can start this. So it was this. Yes, it's exactly the same. No, but the next is with the 3. No, in the power of 2. It's easy to make mistakes here. Power of 2 plus y in the power of 3. Does this make sense?
Yeah.
Yes, it makes sense. I have the multiplying factors from the Pascal's triangle, and then I have to just to know that these powers also are modified. And this is, if I calculate this open, like I did earlier here, I get the same result.
Yeah.
So this is just a shortcut. It's nothing magical.
Yeah.
Yes.
And then you can't simplify that one because it's
You can't simplify anything because there's different base.
yeah.
Or also here.
Yeah.
Of course, I could, for example, take the x as a multiplying factor where, or something where that all the terms that contain x, but it doesn't make it any simpler.
Yeah.
It's the same to leave it like that and ask if you didn't realize what happened. Okay, so then I have something in the power of 4. Now I would need to realize what that means there. Okay, so I write it again here. I have something in the power of 4. A plus B power of 4. And then I have there in the Pascal, I have 1, 4, 6, 4, and 1. And now I would need to know how this goes. Okay. So obviously I have first this in the power of 4. Then I have 4. And now do I have to put the minus now? Yes, first I put the minus. I always first put the minus. If there's a minus, I first have to put the minus. Then I have to put the multiplying factor, that was 4. Then I have to put the first, and that would be in the power of 3. For sure. Yes. Yes. So it's the 1 power down. Then I have to multiply with 3 this next term. But I already have the minus here, so I don't need to use the minus now. Then I put plus. The next one is always plus. And then I would put the 6. Then I put this in the power of 2. And the other in the power of 2 as well. So then it's the same powers in that term. Yes. And then I have to put the minus. This is not something that I will ask you to do in the exam. We just quickly see this once and then you know that there is this kind of a shortcut is at some point. You would need it. So then I have a multiplying factor of 4. And then I put this first without the power. The next with the power of 3. And then I put the last one. So I have minus, plus, minus, and then I put the plus for the last term. And that would be this in the power of 4. Wow. I think I read it correctly now. Yes. I think I take a little bit more space, then I just open this quick. So here I can, of course, multiply these numbers. Minus 12, a in the power of 3b. Then I can put 6a in the power of 2 times, now 3 in the power of 2. So it's 3 times 3 is 9 times 3 is 27. B in the power of 2. Then I have minus 4 or 3 in the power of 3 again. No, what did I do something weird here now? No, that was only in the power of 2. Okay, so that's only 9. So now I could have actually done it. Well, let's put the 9 there. Now it's in the power of 3. So that's 4a, then it's the 27, and b in the power of 3, and then it's in the b in the power of, this in the power of 4. So what is 27 times 3?
Is that right?
What?
79. 79.
Maybe. So what am I doing? Yeah, this. So 3 in the power of 4 is 81. Okay, almost. I think now it's correct. And then I can still simplify it a bit. Yes. Six times 9 is 54. B in the power of 2 minus 4 times 27 is 80. And then it's 4 times 7, which is
28, I think. Is that 7 plus 9?
yeah, okay. I'll just it's very okay. 108 A, B, and then it's 81. B in the power of 4. Okay. Hopefully this is correct now. It's very good. You know, this, like, for sure, this Pascal's triangle has been a really great help earlier on with a bit more complicated calculations, but thankfully nowadays we have the computers.
Yeah.
That's what we could say for the Pascal. Thanks, Pascal. Nowadays we can put your equations to the computers.
So you wouldn't use nothing, a long one at a time. You wouldn't use that.
Yeah. This is the other way to do it.
Yeah.
But we are not learning these.
Yeah.
So this is the same, but we didn't learn what this means on this course at all. Maybe somewhere else you will do it. Because here, if when you do this means this. So you have to follow what it is. From here on, you modify it. Maybe this is, for example, for this kind of simple.
Yeah.
It's still very simple. But you can also from here on, you can check.
Yeah.
Also with this equation, of course, you get the same result, yes? You can do it that way as well if you prefer. Now we just use the Pascal magic.
That's matrices, no? Are those matrices?
Matrices. No, what is it called? Could it be called matrix? This. I think this means still something different. This is something over something, or it's not the matrix. It looks a bit the same.
Yeah. It's just the shape of the
brick. Yeah, I know, yes. But it doesn't. Where do we have the matrices here? Laplace transforms. Arithmetic series. In the series you have matrix. Yeah, this is how this equation book is handling matrices. So it has a bit different kind of it has a straight line here.
Yeah.
Yes. But here actually, when you have really a lot of stuff in, but this doesn't mean the same as this here.
Yeah.
No. Okay. Yeah, this means that you would need to realize that I have a common factor here.
Yeah.
So I can multiply this with this. I can multiply both. This would mean this, yeah?
Yeah.
So here I would need to realize that if I take a common factor, I would get here 32, 36. And now this looks like something. It's like the first one that we did, where I didn't write it, so it's the this dependency. Six. And this is also no magic. If you calculate this, then you get this. Yes. It's just a shortcut. Just ask if you don't realize something. So obviously, again, I have a common factor here, yes?
Yeah.
It's the same for both. Just like earlier, this, like I had it here. So the common factor can be also some kind of sentence like this. It doesn't have to be a number.
Yeah.
Yes. So I write it, for example, first, and then I can write the x minus 1. Yeah.
Yeah. For A, you just need to plug in. So you just take the numbers from the first equation, put it into the,
So I checked with this dependency. I checked that, well, it looks like this, yeah.
and then that's the and. Like you would, if that was an exam question, that would be okay.
Yes.
Yeah, these are-
That would be a good exam question, yeah?
yeah, I would like that.
So here is again the same. That I'm supposed to make it look like this same thing. So this could be also in the power of 2, yeah? With 1 you can do anything. So any of you going to the SSAB?
Okay.
No, nobody's going. So I have to figure out myself where I have to go.
What the accent? B.
Yeah, it's in Rahe.
Ah,
SSAB, yeah. This is also a steel fabric.
Yeah.
Yeah. So I have to know where is the bus.
The like steel fabrication.
Well, maybe it's something that I would need to know a little bit about, yeah.
Yeah.
I haven't been in these places for so long time, when I was a student. That's quite a while ago.
Okay.
So for sure, for me, there's some new information as well. Yeah, I'm supposed to put this away. Mhm. So this again looks similar to this. So now I just have to realize that I have here something like this. This is a bit like some kind of, so this means the same as this, and then it starts to look the same. Why not? It can also look like that.
Yeah. Did I ask for C for 5B?
5B.
Yes.
Okay.
I think that's you're putting it back into the brackets.
And then there is 6A. plus 12. Many things. Plus 6 ay in the power of 2. Okay, so here has to be some kind of a, you multiply something, then you have something. If I take a common factor here, then most probably I would get through, yes?
Okay.
So if I would take 6a
Yeah.
to multiply, so then I would get it's in the power of 2 plus 2x y plus y in the power of 2. Yes.
Okay.
And now this looks the same as the one, the a plus a, not a. Yeah, a plus b. Yeah, of course, a plus b, because that's how it's written in the squared. Is that a plus 2 ab plus b. Yes. Now it's the same. It's just x, y, x and y. So I would have 6a times x plus y in the power of 2. That makes sense?
Yeah. I thought I would, you know, where you go from, you put it back into bracket. But yeah,
Because here is like something that follows the dependency and something that doesn't, because there's no power. So then you have to sort of get rid of it first. But you can realize that it's there in all of those terms. This looks like something again, yeah? So this could be the same as 2a minus 1. Yeah. And then we have this dependency. A in the power of 2 minus b in the power of 2 is a plus b times a minus b. Yes?
yeah.
So now I know that this would be then 2a plus 1 times 2a minus 1.
Yeah. You know these formulas, like you could close your book and you would know them.
Yeah, of course. But then when I started teaching, now it's like my brain works now, but on the earlier years when my son was younger and I didn't sleep in the night, it was very difficult when I started teaching this because the brain didn't like work at all. It's like with the maths, it's completely shuts down
Yeah.
if you don't get any sleep.
Ah, yeah.
You'll see that soon. That will be coming for you. So sorry to say.
I was hoping that wouldn't be too bad. Yeah.
It's really bad.
Mm.
Yeah, it's just like you can't. It's just like
For for 7a, is that something I could, you know, if you go out of the brackets, then you could just cancel out.
So the
Right.
6a, the 6, you are supposed to find the resolve those, basically those equations and see if there are some common factors, yes?
Yeah.
So you have to use the second degree equation. And then in this, the 7a, what is here? One minus 2x. What am I supposed to do here? I can just take a multiplier. So I would have these. I would have this. And then if I take a multiplier here, so that I multiply this with -1. So I would put a -1 here. And of course here as well, so I didn't do anything bad. Like this. And then I would multiply it here. Only inside these brackets. So then I would multiply this with -1. So it would come, this would become, the signs would change, yes, if I multiply with -1. So I have a multiplier here. So I would get inside these brackets minus 2x plus 1, yes? And here I would still have -1 times this. And then if I don't now see that this is the same, I can still change the order, yes? It's exactly the same. And then here I have this -1 times this. Okay, now I've got to the point where I have the same under and on top of the line, yes?
Yeah.
And I can take it out. And now I have here 2x minus 1 and here -1.
Yeah.
So now if I divide this by -1, I divide this by -1, I would get -2x.
Yeah.
And this +1. Yes. Or 1 minus 2x. Because I can put them into another order. Yes?
Yeah.
This is this kind of mathematical tricks.
Yeah.
Sort of. How you can. It's 11. Okay, now I have to run. I have to know where the bus goes. I still don't know. It must be on some. Maybe they'll wait for me. But
We had when we went, but there we go.
it was there.
Yeah.
Okay. Most probably it's there.
I don't want to be responsible.
Me missing the bus.